Chern-Simons action, we'll be working with the SUN gauge group in the large N limit. But we're also going to add matter terms. So there's going to be one theory with fermion, which is going to be the Chern-Simons at, let's say, level Kf. Okay, and then add to it fermion term with a minimal coupling to the gauge. So this is one theory. The other one will be a bosonic theory, which is Chern-Simons at level KB, B for boson, plus 0 E3x d mu phi squared. But this won't be the free boson theory, it will be the Chern-Simons criticals theory, where lambda 4 is taken to infinity in the appropriate way. So this is just to remind us of the Wilson-Fisher. Things we know about them is that large N, they have really nice properties. They're exact CFTs, even if you marginally deform them by the Hooft coupling, and so on. Now, so let's just first talk about the fermion theory.
Sorry, whatever, but you're going to be in Euclidean space. You got that I in the.
Yeah, Euclidean.
Because we compute transpose, so.
Yeah, we compute the correlator in Euclidean space and then analytically continue the usual story. Okay. So the fermion theory has a conserved current, a U1 conserved current, which is I psi bar gamma mu psi. Okay, and what we will be computing is the 2-point function of this current. Now, and which we know gives us transport. So first, let's talk about zero temperature. At zero temperature, the J 2-point function has some Lorentz invariant structure, which we can write down. So just to make sure, the energy dimensions of Jx is 2, of Jt in momentum space is -1. So when we write the Jj correlator in momentum space, it has dimension -2, which is like 1 plus -3. This takes care of the delta function. So overall you have thing of like with the momentum units 1. So you can write down a structure which is Jj of P should be equal to some number tau times P mu, if I put mu here, P mu minus delta mu P square divided by mod P plus kappa over 2 pi epsilon mu rho P. Okay, so this is a parity even piece, this is a parity odd piece, and both tau and kappa can be functions of lambda, the two. So we'll always be working in the large N limit, nf goes to infinity with lambda f equals nf over kf and space. Now, hello, hi.
Oh, hi, Spencer. Hi. Okay.
Right. I'm sorry. No, it's good. I think that
Can we zoom in a bit? Does that help, zooming in?
Yeah, it helps, but I can't keep on doing this and also burning. Those things I understand, I do. The things I cannot follow, that will be bothering.
I think Santa said for the future, right?
Yeah, for the future. Okay. Okay. I'll put more pressure while writing this job.
Okay, please interrupt if there's a crucial equation which isn't coming out clearly. And please do that and we'll write it more clearly. And you have the zooming in, right? We'll also zoom in there.
Sorry for no worries. Okay, so what I'm going to talk about next is this number kappa at t equal to 0. And the existing calculations of kappa, there were answers written down in various papers. I'll come to how we calculate it in a while just to mention it. But for example, the kappa for the fermion theory was written down nf over 4 lambda f times sine square Is that visible to the
With some choice of normalization.
let's say this normalization fixes the dimension of the current. Well, it fixes the normalization of the current, and then that fixes this 2 pi fixes kappa, and there's no and then
You mean psi has the free the usual kinetic
term, yeah.
and everything is free.
Yes, exactly.
And this is in dimensional regularization, for instance.
Yeah, this is the regularization scheme is precisely the subtle issue that I'm going to talk about today. And kappa for the boson is basically the same, but with NB and lambda f replaced by the corresponding bosonic variables. Now, these expressions look fine, and first observe that they are non-perturbative in lambda. So these are not perturbative results. It's a complete function of lambda that is determined by solving some Schwinger-Dyson equation. But what's more problematic is that these answers are different under the bosonization duality. They don't match. The change of variables that you have to do to get from the fermionic to the bosonic theory is that.
I have a question.
Yeah.
You said these expressions are non-perturbative in lambda.
Yeah.
But if I make a small lambda expansion, there is a sign square coming on top.
Right. So you can expand it in series in lambda, and the first term will give you, the one loop answer and so on. But this is like a resummed. It's summed up all the planar Feynman diagrams.
Yes, I know that actually, but you said this is non-perturbative, so that's why I'm wondering. It's also valid in perturbation theory.
It is, yes. I just mean, sorry, I should just say, this is the answer that you get by solving the Schwinger-Dyson equation.
Okay.
Right.
And sorry,
Yeah.
tau, what about tau? What do we know about tau?
Tau was also computed, and there's no mystery in tau. Since I'm talking a little bit about past work, there was no mystery, and there's an expression with a cosine in it, which you can find in papers, and it's there.
And that one is duality invariant.
That one was duality invariant as well. But this one, so first of all, what's the change of variables? Lambda b has to be taken to lambda f minus the sine of lambda f. Okay, so let's just assume lambda f is positive for now, so this is lambda f minus 1. And nb over lambda b, which is the level of the bosonic theory, is minus the level of the fermionic theory. Okay, so this is what you have to do to get the bosonization to work. But you see that if you compute now, if I write here, it's visible. Kappa fermion minus kappa boson. After doing this, you see this is n over lambda, this is n over lambda, so this becomes a minus of the prefactor. Lambda b is lambda fermion minus 1. So the sine squared becomes a cosine squared, right? And they add. So basically what you get is nf over 4 lambda f, which is kf over 4. Now that is not zero. So kappa f is not equal to kappa b. Okay, and this is kf is an integer we know, so it belongs to some integer divided by 4.
In general, the first guy is a sine square. If you express everything in lambda f, the first guy is a sine square, the second guy is a cos square.
Is a cos squared, yeah,
Yeah.
exactly. Yeah. But when you add them, see, you get kf by 4. Now, therefore, you might think, okay,
And whose calculations were these? What?
these are Guy, Gurari, and Hofer, and some in the papers by these Israeli.
But they claim to have everything consistent with the calculations.
No, these fractional parts were sort of missing.
Really?
So, right, yeah. I mean, Guy was, so I should say this is a paper I wrote with Sean Hartnell and Guy Gurari. And Guy is part of the Israeli collaboration who worked on this. And I mean, he acknowledged that this part was.
That there was something that was not.
Yeah, it's not
It was
matched.
certainly not in the introductions and conclusions of the book.
That's right. Okay, so what's the resolution here?
This is not large n, it's large phrase.
This is large n and large k.
The lambda if you just what is the ratio nf by lambda? You define lambda if by
Lambda f is n by k.
but n was the number of flavors.
Okay, so it's lambda f is nf by k.
Yes, yes. Yes, it is.
What?
So
No. NF is number of colors for the fermion.
number of colors.
Oh, colors.
There's no
Colors,
flavor.
not flavor. There's just one
Yeah, yeah.
flavor. flavors. Yeah, sorry. Yeah, NF is SUNF. The gauge group is SUNF and SUNV. I'm just keeping it different because of the thing. Okay, so the answer here lies in the fact that these answers are not complete because they are missing contributions from the parity anomaly. So let me just write the full answer.
Sorry, 1 minute.
Yeah.
Maldacena and Gibolev had this general structure for correlators. Did the answers that you wrote down without this additional term agree with their general structure?
Yeah, the structure is I mean, at zero temperature, the structure is just like Lorentz invariant.
The structure, including the coefficients.
Right.
Or they only had results for
the tensor structure.
But they didn't have results for. I suppose they only had results for 3-point functions. Once the 2-point functions were appropriately calculated.
Right.
No, but they must have had results for the ratio of those two, tau and gamma, right? That's an invariant.
Okay.
So this must not even be. If you're saying the right answer has a shift in kappa b, then the old answer must not even be agreeing with Maldacena.
Okay.
So they must have known they were wrong, but they didn't admit it. Okay. Okay.
Sorry, Maldacena and Gibolev, when they did this general analysis, they wrote down the 3-point function, right?
They wrote down the 2-point function and the 3-point function. So then they only talked about they normalized the 2-point functions in a certain way, and then talked about 3-point functions because they were doing abstract analysis. They didn't have an a priori normalization. So the overall 2-point function you can't talk about in their language. But if you have two different structures in the 2-point function, you can talk about that.
Was the ratio was fixed of tau?
Everything was fixed. Everything was fixed.
I don't know those papers actually too well.
Yeah.
Okay. And but also this answer is changed. It is not full. This is an NF lambda f by 4 plus NF by 2. So okay. So now when you take these expressions and you substitute this, they actually match. Okay. They match. Not exactly, but up to an integer. So this factor of 4 goes away. Okay, so let's say after you do this, you don't get this, but you get something that is an integer. And now let me explain why that is like
A
this.
small integer or a big integer? Which is like an integer like k.
Yes, that will depend on even these numbers you can change by integers. By using your calculator.
Matter.
Yeah, exactly.
It's the typical thing that the phrase.
Right, so let me just explain the contact term type. So how you generate correlation functions of J is to add a background gauge field, B mu. So E to the minus some effective action.
So just a Chern-Simons term for this.
Yeah, for B mu.
Yeah.
Exactly. So in the effective action, so normally we would just write this as D psi bar, dA, e to the minus s fermion.
But for gauge invariance, that has to be quantized. And therefore, you can shift back.
Yep.
Yeah, I see.
This would be plus G mu, B mu. But you can have terms maybe that is something here, B wedge dB. Okay, and that coefficient you can choose because it's a term that doesn't involve the dynamical fields of the theory, but only involves term that's like pure gauge.
So I'm going to withdraw something I said. Maldacena and Gibolev always, what I didn't realize was that you will ignore a contactor because there's an analytical momentum. Maldacena and Gibolev only looked at correlators at separated points. So they would have been insensitive.
Okay.
Sorry. The structure here was epsilon times P,
P, which is
contactor.
Okay, so how do we fix that coefficient?
Yeah.
Okay, I see.
So how do we fix that box? How do we fill this in? So maybe let me just tell you. Okay, so just to complete the story, the JJ correlators are obtained by delta B. So we have it. If we want to get the 2-point function of J, we make two derivatives with respect to B, and so this term precisely gives you a momentum with an epsilon. So the kappa is shifted by this coefficient, just it gets shifted. So how do you fix it? Is by one way to do it is to do it by an RG flow. So let's just talk about free fermions. So let's forget about lambda and just take a free fermion and compute the JJ 2-point function for a free fermion. just a one loop answer. It's this.
What you were trying to fix now? The difference between the...
This number, what should this be?
Yeah. Or more precisely, if you add that, you can add that for the bosons and for the fermions, and it's the difference that you want to fix.
Yes. But what I'm claiming is that I can fix it for the fermion theory by using some principles without any reference to the boson theory.
Okay.
So now I have a free fermion, but I give it a mass. So it has a mass term, and it can flow from UV theory, which is free, to like a completely gap theory in the infrared. Okay, and I can compute this diagram. It's just some gamma. So this will be some integral d3q gamma mu q dot gamma plus m over q square plus m square gamma mu q minus p dot gamma plus m by q minus p square plus m square. Okay, so we can compute this and isolate the epsilon tensor part of it, because that's what I want to focus on. The epsilon tensor will come from 3 gamma matrices, trace of 3 gamma matrices in 3 dimensions epsilon. So I can just isolate that term, which will be epsilon mu mu rho p rho m over mod p 1 over 2 pi sine inverse mod p over square root of p square plus 4m. So this is what you get when you just look at this. Now, what I want to do is look at the UV limit and the IR limit of this. Okay, so in the IR, the mass is much bigger. Okay, so the mass is much bigger here. So it becomes P over M, which cancels this M over P. So you get like kappa equals a half.
So this is the usual story. Integrating on a massive fermion generates
Yeah,
kappa equals
it
half.
generates a kappa equals a half.
Okay.
Right. This is precisely okay. So now let me just
to
complete the laws here. In the UV, it's the P which is much larger. So this is sine inverse of 1, which is pi over 2. But this term goes to 0. So in the UV you get 0. Now, what the logic that I want to give is that in the IR you should expect kappa to be 0 or an integer, because it's a gap theory. So there should not be any dynamical, because this is the Hall conductivity of the theory. So you actually put in a half here for the free fermion, so that the actual answer that you get is here is actually 0 plus a half, and in the IR it's 1 half plus 1 half. So this is what this half, putting a bare 1 half allows you to do. There is some contribution coming to this loop just by integrating out the fermion, and then there is something that you already added in the action to begin with. So the combination of those two makes you okay. So now by adding this 1 half in the UV, we have some dynamical Hall conductivity, which is this 1 half, and the IR we have gotten rid of it. So that's the origin of this NF over 2. NF is the number of individual fermions, and the 1 half is the 1 half here. But you get corrections because there's a Hooft coupling also. So you can do this computation at 0 temperature. Again, solve the Schwinger-Dyson equations with a mass term, and repeating that with this same exact procedure, but solving those Schwinger-Dyson equations in the light cone gauge in the presence of the mass for both the fermion and the boson theories will give you these two terms.
Wait, but now you could compute this kappa F minus kappa P, right? Just a computation.
Yeah, now we can compute it from here. And it will be something that's proportional to N.
NF?
NF, yeah. Or, they're both proportional, NB is also. So and it depends really, because you could have put minus half here.
So this is just telling you, it's telling you what the suppose I decide to deal with a particular boson current, it tells me what the dual fermion current is, right? It tells me the definition of the fermion current.
It tells you the definition.
Suppose I want to deform the boson side by a BU.
By this kind of a term.
No, by BU, so J mu BU.
J mu B mu, right.
then I want to know what the corresponding deformation of the fermion is.
Fermion side.
So what you're telling me is that if I deform the boson side with a J mu B nu, I have to deform the fermion side with a J mu B nu
Plus exactly.
something.
Exactly. Right.
Okay. So it just tells you what the duality
What
map is.
what the duality map is, what the proper counter term.
Yeah.
Right. Exactly. Yeah. And it's these terms that, you know. And how we actually came to these terms is interesting, and they're like totally confused, the answers are not matching. There are papers by Subir and Kedar from the early 90s in which they computed for U1 Chern-Simons perturbatively in lambda the 2-point functions, current 2-point functions. So if you expand this perturbatively, you get a pi squared plus 4. And here you get a pi squared minus 4. And these answers are there in their papers, and you're like, what quantum field theory calculation ever gives you a pi squared plus 4? It's like, you know, normally you get a pi squared or, you know, some rational thing. So yeah, this gives you a pi squared and plus 4. So there we thought there's something to do with, you know, anomalies and so on. And actually if you plot the conductivities, you know, numerically, they look very much the same as plots in their papers. So perturbative U1 Chern-Simons, the shape of the plots is not very different from like large and exact solutions in lambda.
By the way, these recent papers by Seiberg and collaborators and other people, the shift, this contact term shift was very important.
Yeah, and it's inspired by their work. I mean, they had it first, and I mean, because I'm like very bad at giving references in talks because I just flow with the thing, but it's their work that we are following. Exactly. Okay. So now this was the zero temperature part of the story, which sort of fixes this, you know, small glitch in the duality. Now let me move to finite temperature calculations.
And then just, because this is a vexing question that often comes up, just from the structure of the CFT, that is, if you require the 2-point function to agree with limits of higher point correlators, including up to contact term, would that have fixed the contact term as well? Here you added a mass and integrated out, but just from the...
Yeah, that's a good point. Like if you sort of reduce the 3-point function in some limit.
Yeah, I mean, the trouble is that the OP doesn't care about contact. I mean, you know, you're away, x is not equal to y, and so you're not sensitive to contact terms often. But okay, it would be nice if there was some argument in
Some
there.
argument.
There's not always an argument like that, I think.
It sounds like it relates contact terms to contact terms.
Yeah, yeah. It doesn't relate now. But maybe some, I don't know if that consistency is strong enough to fix it.
In this particular case, I think that the belief is that if you just take the generator correlation functions on the bosonic side, on the left hand side, on the fermionic side, all you have to do is add a B wedge
With the appropriate coefficient.
with coefficient. That's purely quadratic. So the only thing it would do is that. So
In the 2-point function.
in the 2-point function, I think.
Not change anything else. So there's a genuine sort of freedom.
I think.
Right.
Yeah.
And you're saying with this choice, the duality map works.
Right.
That's what I'm going to do.
Exactly.
But
Okay, great. So now let's talk about finite temperature calculation, which is what we started out doing to begin with. So, by dimensional analysis, again, this, let me write down the Raghu formula. So, sigma mu nu, the conductivity, is equal to the retarded Green's function of J nu, evaluated, for now, let me write complex frequency set. There is a subtraction term by IC, and we have to put C equals omega plus pi. Okay.
sorry, what's the subtraction term?
It's and this is actually very important also. So this is at some. Okay, and of course, how we do this calculation is there is a complex
They
frequency.
won't be able to see. I see yes, won't be able to see.
There is a complex frequency plane, the Z plane. Okay. In Euclidean computations, we evaluate the correlator on the imaginary axis, the Matsubara frequencies. Okay. And then we just analytically continue, and if omega is somewhere here, then this this gr mu nu z is the same analytic function evaluated, let's say, just here above. And what's chi? Let me come to this now. So I'll do a little segue into Fourier representations of various correlation functions, because I think it will. That's the main point that I'm getting at. So before that, let me say how the J mu correlator is evaluated, just for completeness. People here know it very well. So first, you work in this light cone gauge, which is A plus equals A1 plus I A2 equal to 0. This gets rid of the cubic term and makes the gauge propagator very simple. You add up all the rainbow diagrams to get the fermion propagator. This gives you the fermion propagator S. Then you compute the vertex, the exact vertex, which is equal to the bare one plus things like this. And where now each of these propagators can be the full propagator, what you computed here. So this is the set of diagrams that you do to compute the vertex. And then in the end, you just compute the complete the loop with one bare vertex and one full vertex, and these are the exact problems. Okay, so the details of the Schwinger-Dyson equations are there in the paper.
And you do them at this as specific kinematical moment. If the momentum going into the loop
is zero, that I should say that. So for the conductivity, all you need is spatial momentum 0, and we would not have been able to solve these equations at a finite k. So k going into here is 0.
But
Omega is not, yes. And these guys actually, since it's a CFT, will only be functions of omega over t. No other scale will come in. So t and omega are not independent but appear in this way. So the previous t equal to 0 calculations are equivalent to omega equals infinity calculations. Okay, so these are the Schwinger-Dyson equations you have to solve, and you get. So the first point that I want to get into is the zero frequency limit of this guy, which is the DC conductivity. More specifically for sigma xx. So we are looking at the longitudinal conductivity.
Massive or massless fermion?
Massless. Now we are back to massless. The mass was just to sort of fix this. So we are in a CFT, there's no mass.
And the holonomy eigenvalue distribution is stable now.
Exactly, yeah, exactly. Yeah. So the order of doing, the loop sums here is you do the Matsubara sum, then you do the holonomy integral, and then you do the angle integral, also in the plane, and then you're left with a one radial momentum integral, which is left as a numerical, which is done numerically in mathematics.
And your chemical potential
Is 0. Yeah, mu is 0.
This is the order for that last thing.
There are also loops here.
So all loops you do in this
In
order.
this order. Yeah.
So you have various radial integrals that come at various.
There are two left, one from here and one from here. And so in the end, the expression is a double integral, the two-dimensional integral, which is done numerically in mathematical. There are some limits you can evaluate analytically, like the perturbative limit and so on. Okay, so in the DC limit, sigma xx is interesting because it's infinite. So what I'm going to tell you is that sigma xx at omega has something that looks like some coefficient d times a delta function of omega over t, and then it has other contributions. So we are going to get into the physics of this delta function, like why is it there, what does it mean, and so on. First thing, it would go away at finite n. This is only a large n artifact because the theory is essentially free at large n. The fermion particle cannot decay. Okay, so let me first start with a Fourier decomposition of the Euclidean JJ two-point function. So the G Euclidean at time tau, which is the expectation value of e to the tau h j e to the minus tau h j at some temperature beta. So this is j of tau. Okay, and a spectral, I'm going to omit the 1 over z, just sum over the double sum over the spectrum, e to the minus beta en, e to the tau en minus em. Okay, can Fourier transform it. It's a periodic function of tau, so I have to do this periodic Fourier transform. So GE at omega k is equal to integral 0 to beta d tau. Let me GE tau e to the I omega k tau. Okay. And I can do this integral, and this will be equal to sum over n and m j n m squared e to the minus beta en minus e to the minus beta en divided by I omega k plus en minus en. Okay, so we can just see this integral is very simple because you have to do the tau integral and tau only appears here and here. So this denominator works out this way. But you get contributions both from the upper limit and the lower limit. The upper limit, this e to the minus beta en becomes this, and the minus 1 becomes this. Okay, so this is just the spectral representation of this guy. Now what is chi? Chi is just this thing with omega k equal to 0. So maybe just let it write. Chi equals GE at omega k equal to 3. So it is the static susceptibility. It's like a thermodynamic quantity that you would compute at 0 Mansubara frequencies. Okay? And by setting this equal to 0 here, you get some expression for it. Okay? So now let's analytically continue and write down the expression for GR of Z. Okay? Let me just erase this and write
So I
it.
guess, I mean, if I open lambda evolutions, oftentimes I don't have the chi mu term there because many materials don't have static susceptibility.
Yeah, because normally, for example, even in fermion, free fermion, this is 0. The JJ susceptibility is 0. But I mean, you have to be ready. For example, for a free massless boson, this term is non-zero, and you really have to subtract it. The place where I found the derivation, the most convincing derivation of this term, is a paper by Luttinger with the title "Theory of Thermal Transport Coefficients." In that, he really takes the pain to solve the linearized, perturbation equation, the time-dependent perturbation equation, and get this term. Okay, so but
In hydrodynamics, is chi mu 0 or non-zero?
in hydrodynamical theories of, let's say,
If you compute the correlation formula, sigma mu, at the moment the left hand side means just a definition, right? So you can define it to be whatever you want.
right. So
what's
the
the
independent definition of left-hand side is if you apply an electric field,
Yeah.
J mu is sigma mu nu times E mu.
Good. So now if I compute this quantity within hydrodynamics,
Sigma mu nu.
yes, in hydrodynamics, I've got a fluid, I turn on an electric field, and I measure what current I get.
Right.
I will get something. I can also compute the retarded correlator within hydrodynamics, and I can look at the relationship between the two.
And what's the first calculation? I mean, in hydrodynamics, it's an input, right? Some of the coefficients you have to input.
Okay, the material parameters I input, but this is not a material parameter. This is a question of a response of the system. And this, for instance, is a function of omega.
Yeah. So, for example, the DC conductivity you have to input in hydrodynamics, right?
There's a number that's an input.
Yeah.
In terms of that, you get functions of omega.
Yeah. So, yeah, exactly. So that number, for example, the static susceptibilities would be one such input to the hydrodynamic.
Okay, suppose I give you the equations of hydrodynamics. Those are some given numbers. I don't care what they are. You call them what you want.
There's some viscosity.
Some number, viscosity, whatever form.
Let's talk about, let's say, maybe computing the shear viscosity instead of the conductivity.
That's it.
Yeah.
That's it. So now I give you, the Navier-Stokes equations with some particular viscosity.
Yeah.
What do you call it viscosity? Some number. Okay. Now with those equations you can compute whatever you want.
Yeah. I agree. Yeah.
Okay. So you can compute sigma mu nu as defined in the first line.
Right.
You can compute G mu nu r as defined in the second line.
Yeah.
And you will find that these two are not. That these two are.
They differ by this chi mu nu.
And chi mu nu is so non-zero within hydrodynamics.
It depends on the theory. Depends on the
the
underlying
theory is-
microscopic theory.
No, I'm telling you, the theory is hydrodynamics.
Well, then chi mu nu will be some set of parameters which are input. to your thing. So for example, the shear viscosity.
I've given you a shear viscosity. A shear viscosity, a number between. Okay.
For example, in such a system, even in this theory, if you compute the static shear viscosity, it will be infinite. You won't be able to write down hydrodynamics for strictly large N Chern-Simons-Matter theories. The dc eta is infinite. So therefore, your starting point, the equation of hydrodynamics, the eta that's sitting there, is in the assumptions that go into writing down those Navier-Stokes equations. And if eta is infinite, then
see, let me ignore the assumptions. I give you a Navier-Stokes equations, they're totally well defined. The parameters are just numbers. Just numbers.
yeah.
There's no omega dependence, no infinity.
Yeah, but eta is some, let's say, 3.1 or something.
1 over 4 pi, let's say.
Okay, yeah.
Okay. Now I use those equations to compute anything you want.
Yeah.
I want to know whether the first line and the second line will agree with or without the timing. So I can compute G mu nu R.
Yeah. So let's not talk about this Chern-Simons-Matter.
Yeah, just hydrodynamics.
Just hydrodynamics.
Just hydrodynamics.
You will need the chi mu nu.
I will need a
Yes. Yeah. Perfect. Okay. So this is this. So what is now? Let me also write down a spectral representation for GR of omega k. So it's very simple. I basically just have to copy this guy, and you see these crosses were at I omega k, and I just replaced the I omega k by omega plus I epsilon. It's the same exact expression here.
If hydrodynamics gives this, I can't believe lambda evolution says that.
What I mean by that is if you open at least the beginning parts of Hugo formula derivation.
In lambda evolutions or an inferior.
No, don't go to it. I think I looked even at Landau Lifshitz and didn't find this, but maybe I looked at it.
There are old books that have this. I have a book that has it.
No, I mean, he's challenged. My memory isn't good enough to say whether.
No, but I mean, it's some very subtle thing I can imagine Landau missing. But if it's something that shows up in hydrodynamics, I can't imagine that it's missing. Meaning that is not a subtle thing. Okay, it's just
No. So I really urge you to look at this paper by Luttinger. This is from 60s. He just derives it, solves the linear response equations and gets this done.
But by the way, if it shows up in hydrodynamics, I would derive this using hydrodynamics. That's the simplest way to do it. Because
Some of us are more familiar with Kubo than with
the best derivation Kubo is through hydrodynamics.
I took your whole lunch. Sorry,
Maybe we can
my education. At least inferior books, I'm sure. There's an inferior book going around in the student room. Book doesn't have
so like throughout multiple projects in my PhD, I've struggled to sort of come to terms with what is the difference between chi and gr and whether this delta function goes out of the window if chi mu nu is just the zero frequency limit of this. Then in zero frequencies just cancels. This doesn't make any sense. But they're actually different, as I will just show you. The delta function comes because the denominator is zero, and these two things are different as frequency.
So very, very nice.
Yeah. So what is this? I omega k is omega plus I0 plus En minus En. Okay, so I just write this. Now you see what's the crucial difference between these two things. When I take omega to 0, I put this 0, and you see the numerator and denominator are both 0 for degenerate states.
I'm sorry,
Yeah.
I'm a bit confused. I mean, the top line is the retarded.
Retardation.
The GE was just something you defined,
It
right?
was a Euclidean Green's function.
Was a Euclidean.
Euclidean time ordered formulation, which is the periodic, periodic with period. So it has its Fourier transform only has support on those crosses.
Yes, on the omega.
Right. So now you see if I set omega k to 0, in this fraction here, for degenerate states, let's just consider degenerate states now with energies equal, the numerator and denominator are both 0. Right? So you get some finite contribution from the degenerate states. Whereas here, you don't because of this I epsilon. So when you take degenerate states here, the numerator vanishes, but even if omega is 0 and the states are degenerate, the denominator is non-zero because of this I epsilon.
So you get 2 pi delta. It's the principal part which probably vanishes plus I pi delta.
Yeah. No, let's just not even go there. Let's just say it's non-zero because there's some I epsilon. There's an epsilon which is there and it's not here. So this is 0 divided by something non-zero, something purely imaginary. This one is 0 divided by 0, which gives you some finite thing. So if I write, erase that. So chi is actually bigger. So because chi has more contributions. So chi minus g retarded at omega equal to 0 is equal to sum over n and m with energies equal of j n m squared e to the minus beta en times beta. Okay, where did the times beta come from? I just Taylor expand en around en. So the denominator cancels and you get a beta. So this is a very concrete expression for this difference that appears in the numerator. And this is precisely the coefficient of the delta function. Because here you will put z as omega plus I epsilon, and what you were saying, it will give the principal part plus the delta function. So the numerator here, as the frequency goes to 0, is the Drude weight up to like some factors of temperature and phi or so. So this is this d. It's a very concrete spectral representation for this guy.
I see your algebra, but I don't understand it. Skip 2 minutes. So J and M was the matrix
n squared,
of J between N and M.
Yeah.
And you're saying that if there are, for instance, N always contributes.
N always contributes, yes.
Okay. And now I want to understand why one of these contributed. I mean,
Yeah. So let's just see, right? So if Em equals En, the numerator is 0. This is 0. Omega is 0.
so it actually, why did we get an e to the power minus beta e minus e to the power minus beta e?
Because there was an integral from 0 to beta.
Ah.
And there was a e to the minus, So let me, should I write?
I'm sorry. So I think I understand. At least for the downstairs thing, I understand.
Yeah. For this you get.
This and you got that.
And that I just got by analytic continuation. I just replaced I omega k with omega plus I0 plus. It's exactly the same with, this and this replaced.
So now, what you're saying is I've got an analytic function.
Yeah.
And because on the Euclidean space, you didn't have to take the limit to omega goes to 0.
Yeah.
You were actually at 0.
At 0, yes. This is at 0. Exactly.
Because it was discrete.
It is, yeah, exactly. So this function is actually discontinuous in the neighborhood of 0 complex
So
frequency.
you're saying the limit omega goes to 0 is different from
Exactly.
omega equals.
Exactly. Perfect, yes.
So it didn't really matter about which way you took the limit.
Yeah, exactly.
It's just
So if you look at the complex function here, it's 0 right at this point, but it can be something else, just in an immediate neighborhood of that point.
eyes.
Yeah. So for example, for a fermion, it's 0 at omega equal to 0, but it's equal to a half everywhere else.
I see.
In the neighborhood. Yeah, exactly. Yeah.
Excellent. And so now you're saying that this chi only gets contributions from these kind of modes.
Chi minus gr to be precise. This difference, which is called the Drude weight, is actually very well studied quantity in integrable systems literature, because there they always have these infinities because of integrability and so on. So this is a concrete Fourier expression for the Drude weight. Let me write another expression which is probably even more intuitive.
And why was this chi minus t? I'm sorry,
I'm just computing the difference, right? Because that's what appears in this Kubo formula. And I mean, of course, there are contributions here which are from non-degenerate states, but those are exactly the same between this and this.
So everything interesting you're saying comes only from the degenerate states.
Interesting for this purpose.
Wait, I thought this part, sigma minus
gr.
Yeah, gr minus chi was sigma mu.
Sigma mu. Yes. This is precisely this.
So sigma mu gets contributions only from
degenerate states in the DC limit.
In the limit omega goes to 0.
Yeah.
Well, degenerates are diagonals. Even diagonals.
Diagonal I'm counting in the.
Right.
Exactly. Now you see, if this quantity was just 0, and you assume an analytic expansion of this guy, then the first term is proportional to z, and you just get some number. for the DC conductivity. But here we have a delta function, and what we're talking about is the coefficient of the delta. And the coefficient of the delta function gets contributions only from the generator. I mean, the whole thing already like smells of like, happens only in like free integrable system. So anyway, so let me write in a time domain expression for t.
And so here this delta function appeared to be because of some analytic continuation issue from Euclidean to return. But suppose
This delta function? Yeah. No, this just comes from here.
No, I agree. But the way you explain that is through. What I'm saying is that suppose you had an ab initio calculation of the retarded correlator itself.
Yeah.
Then what would this argument be? I mean, you just find that there.
So firstly, if you just computed gr of omega ab initio, you would have no information about what chi is, because as I just said, the function is discontinuous right at omega equal to 0. So you really need to compute the static susceptibility separately, because you see this function is half everywhere else, and just at a point it's equal to 0 or something. It's discontinuous right at that point. So you would need to do at least 2 separate calculations, like one for this and one for this. And of course, in the paper we don't calculate this kind of sums. It's just not for this computed through Feynman diagram that you see.
Even there's still something. So I understand the argument for why chi minus g of r is this, and then if I were to compute the right hand side as defined there, I would get d times the delta function.
Exactly.
But I still haven't understood, I think what Shiraz was asking, which is why is the right hand side what appears in j mu equals sigma mu? Is that supposed to be?
That is what I'm saying. I urge you to look at this derivation by Inglatinger's paper. Yeah, exactly. Yeah, as a yeah. So very clear. Or this book by Foster also. In a different. Okay. So this is it. So now let me write a time domain expression for d.
Various people have told me that I need to get a better edge. Although they disagree in the content.
I think I'm understating this, but it was like really like 3 or 4 years trying to like really understand this difference.
My first question would be: can you see through hydrodynamics? If so, then it's okay. It's either yes or no.
Okay, so let's say
Let me know.
I only have a few more points to make, and
go on.
okay, so what's
It's partially complete the education.
Depends on the Foster is in the inferior group.
All books are really compared to that. It's a fine match.
Spenta and so on can't join us for lunch, so we will. Anyway, so while Shiraz will complete our education, we will transmit that in case it's of any use. All right, okay. Go ahead.
And basically you take the real time correlator here, which is just the Whiteman correlator. Okay. Yeah, the way, you can see this again, if we insert a complete set of states between, left and the right. Let me just write the algebra, I'm not reading too much to say that this works.
This is Euclidean to not.
No, this is Minkowski time. So see, it's a large time limit of some average of the correlator. I'm averaging the correlator from 0 to t0.
No, sorry, but the left hand side is some quantity you're defining.
I'm claiming this spectral expression is equal to this. So if I expand this up, yeah, d is this. Okay, let me erase this.
I guess at large time only the same frequencies will go.
Exactly. That's the argument. Because this 1 over t0 is going to kill anything that does not grow like t0 here.
Yeah, discretize and you'll see that.
Yeah, exactly. So you can see that this is the same as this. Now what does this represent? This represents the piece of the correlator that's not decaying in time. Right? So there's a piece of it which is constant. This t0 and t0 is cancelled. So it's really saying that not all the current is decaying away. There's some part of it, I disturb the system, I hit it, I set up some current. Even at very, very last times, it's not decayed to 0. It's a non-dissipative system.
This is not translation invariance.
In this case, actually the translation invariance argument is not enough.
I see.
Because if you added 1 over n corrections, this delta function will go away.
That is what I was confused about. Sorry, now another remedial question, which is in any translational invariant system, I mean, you've already said P equal to 0.
Not any translation invariant system. Any translation invariant system which is not particle hole symmetric. Here the chemical potential is 0. So you can have that argument of translation invariance does not apply. Why it's infinite is because the system is essentially integrable at large n. So let's take just free fermions at 0 temperature, 0 chemical potential. We know that its DC conductivity should be infinite. Right? It's translation invariant, that's a separate issue. But also, it has particle hole pairs which are equally symmetric. So the current can actually decay.
You're saying that are there states which carry momentum but no current?
Yeah. In this case, actually, let me now even.
Sorry,
So-
just to
yeah,
slow
yeah.
down. Because this comes up
Let
so
me
many
just-
times and I've never quite
Yeah, yeah.
understood it.
So let's take a translation invariant system
Yeah, we take a translation
which has
invariant
particles and
system.
holes.
Yeah, particles and holes. And now,
Like graphene. Let's talk about graphene.
now, if the momentum, if you have carriers which carry charge that also carry momentum, doesn't it prove that
So-
some of the charge current can't decay because momentum can't decay? I mean, so what is the?
So imagine there's a plus charge going this way
We will have a state can current but no.
and a minus charge going this way. So this is a state.
Yeah.
Okay.
Then
Right. So now momentum is just 0. So one way to conserve momentum is just to keep it 0. But these velocities can individually go down to 0. Right? So let's say it's going at 10 meters per second and this one's going at 10 meters per second. I can dial down both of those velocities together.
Okay.
Always have 0 momentum, but have current going to 0.
Okay.
See, the current value here is charge times 20 meters per second.
Okay.
So the charge is decaying to 0, while at no moment am I violating momentum conservation. So this is an example of a system which is translation invariant, in which the current can decay to 0.
Excellent.
And therefore it will have a finite DC conductivity.
But at a finite chemical potential,
This won't be true. Yeah, exactly.
So zero chemical potential.
Yeah, 0 chemical. It is saying that the electron and positive. Sorry.
Connect the line. So therefore, you're saying you won't have a delta function here. Is that right?
If you only had the translation invariance argument, it would not be sufficient to conclude that there is a delta.
Because at zero frequency, where was the frequency here? When you said when to zero, I didn't quite, sorry. Maybe you can tell me over lunch, but we are arguing whether there is a delta function in omega, right?
Which is the DC.
And then you're saying, okay, I'm going to just look at DC currents and ask whether the current can go to zero.
So the long time behavior of the current is tied to the DC conductivity, right?
Yes.
So if I imagine not applying an electric field for the entire time, but just giving the system a kick
Yes.
initially and letting it go, the signature of a finite DC conductivity is that the current that you set up will decay to 0 with like something like e to the minus sigma
At
t.
least here is you're saying that's consistent with momentum conservation.
Exactly. It's consistent with momentum conservation. But on top of it, we have an integrable system, or an essentially free system, because of which the delta function comes up again.
I see. You're saying, You're saying the particles will do that thing, the holes will do that thing, neither decay.
Neither decay. Yeah, exactly. Neither will decay. And it's because you can't cut this, the fermion propagator, you can't cut it and put it on shell.
Yeah, so it's essentially trivial to point function.
It's a, for example, a diagram at like subleading order in n, which will contribute.
Mean free paths are order n.
Exactly. Mean free paths are order n. And so this kind of a diagram in the fermion propagator will, cause damping, but these are down by 1 over n. Okay, good. So now I can also put an inequality. I can put a lower bound on D. Because essentially, equal time correlators define a Cauchy-Schwarz, they define an inner product, so I can write a Cauchy-Schwarz type inequality. And I can insert conserved operators. Conserved operators are nice because Q of T will be equal to Q of 0. Okay, so I can write an inequality, the sum over some conserved set of charges are any conserved charges in your system. J, QA. This angle bracket refers to the thermal expectation value at equal times and with k equal to k set to 0 times CAB, QB dagger, J, and the CAB is some inner product of QA and QB. It's some positive definite matrix.
So what was QA again, please?
QA is any conserved operator. QA.
And in our situation, what will this be?
This will be the higher spin currents. Set of conserved.
They conserve currents or charges?
Conserved charges, sorry. The zero component of these guys, whose dot is 0. So any operator whose time derivative is 0 is good to go in this input. So
what are you doing? You're inserting a complete set of eigenstates of these charges in
yeah.
state. Okay.
And I'm throwing out everything that's not conserved, so therefore there is an inequality. Okay. So for example,
Actually, I have another. What are you inserting again?
Operators,
What?
right? Your
Yeah,
these are operators, right?
so let me write.
These are operators.
So I can expand.
Decomposition of identity. And what is it?
No, but that's some
Yeah,
difference in terms of these operators and
So you write the operator in terms of these Q's, right? So you write J. You can expand it. So you take a Q's which are orthogonal with respect to the inner product, as some coefficient alpha A, QA, plus some orthogonal B's, plus some, let's say, J prime.
Wait, for instance, J was a local operator, Q is some charge. It looks like very different things.
So J here is the spatially average J, is the K equal to 0.
Okay, but it's also J was a function of time, Q is not a function.
Yes, because it's conserved. So in the expectation, QA of T is just Q of 0.
So you're looking at the zero momentum part.
Zero momentum part,
R
exactly.
J.
So this is just zero momentum, zero frequency.
Yeah. Okay.
So when we write this, right, so and just substitute this into this time ordered correlator. So you see the JJ will become alpha A, alpha B times QA, QB in a product.
See, I'm just not understanding the structure of that equation. You're writing
So J, think about the linear space of all the operators.
linear space of what kind of, are we restricting attention to operators that are not functions of time? Or just arbitrary operators in Hilbert space?
Arbitrary, let's not, the Hilbert space, let's just pick some time t equal to 0. Time t equal to 0. Let's say if we have a finite dimensional Hilbert space,
Let's suppose.
there is some set of matrices which form a basis for the space of operators.
Good.
I can just add them and they span the space of operators. But I pick these QAs,
Okay.
which I know when I evolve with e to the iht will be conserved in time. And I pick an orthogonal set of them.
Orthogonal under trace.
Under this inner product. No, under the inner product of two operators is the expectation value. So inner product AB is equal to 1 over z beta trace e to the minus beta h AB.
Yes.
This defines an inner product. So values inner product as well can check.
Okay.
So under this inner product, I pick some orthogonal set of conserved charges, and then everything else is J prime. So now I go in and I plug this expansion into here. Where this JQA is coming this is basically alpha. Right? Alpha is inner product of J and Q. And the CAB is coming from what will remain, right? QA and QB inner product will remain here. And this alpha B is what is this? So I mean this is just it's called the Mazur inequality. Right? It's known in the integrable system literature also. Okay. Good, so this means that as soon as I can find one conserved charge which has non-zero overlap with the current, I know that this quantity is non-zero.
Because everything is time independent.
Because everything is time independent. So now, in translation invariant systems, let's say at finite chemical potential, Q can be the momentum, in which J and P have a non-zero overlap, and therefore it's enough for you to conclude that D is non-zero, and hence that sigma, which had a delta function.
say this again. You said at finite chemical.
Yeah, so just to eliminate that particle whole caveat.
No, but say it again. I thought you didn't have a delta function of a finite chemical potential.
No, you
Always have a chemical.
You always.
Yeah, right.
Because there's an asymmetry, you can't annihilate.
Because when you have a current, it won't be that half the electrons are going this way and half the positrons are going this way. It will be more of the electrons are going this way. So you'll always have some moment. So it can't be.
Yes.
Alright.
See, but here, what's a candidate QA? It's not the momentum. As I said, because the chemical potential is zero. So a candidate QA is like the spin 3 current which exists in the field. The spin 5 current, the spin 7 and all those things. And you can actually find
Some of these higher spin currents are of this sort.
Out of this sort.
Very nice. That explains.
Yeah, that explains that why there is this delta function. Yeah.
But wouldn't they have arrived at that kind of thing from here? This mode expansion of D. I mean, in the sense that if there are conserved currents, then these are the energy eigenstate matrix elements of J.
Yeah.
So you could use presumably the charge eigenstate matrix elements of J.
You have the right intuition. There's a sentiment that once you have these conserved charges, you can simultaneously diagonalize H and Q.
Yeah.
And the J having an overlap with Q is like J having a non-zero matrix element with some of the Q eigenstates.
Right.
And therefore you get like non-zero contributions from these guys.
Right.
You're saying this ensures the presence of this ensures that there are degeneracies.
There are degeneracies, yes.
But I'm just not confused. I mean, the spin 1 current itself is conserved, right?
No, the spin 1 J.
Isn't it itself?
Yes, but in this you have to. No, in the self thing doesn't matter. You have to.
When you try to expand it, do you get any other? I mean, isn't the complete set such that you have spin 1 and then higher? So when you expand the spin 1 itself, you don't get the highers in your decomposition, and then are you trying to explain then those inner products are only there?
See, there's this one set in which you could include J. You could have it, but I can just pick a different set. It starts with the spin 3 and so on. There's one presence of one guy is enough to ensure that this thing. I didn't even have to pick a complete set. Let me just pick the spin 3 current here. Alpha times Q plus whatever. Q3, and then whatever. And that's enough for me to conclude that this guy is not zero.
And just to make totally sure, the expectation value of J times momentum is 0.
J times momentum in this theory is 0. At 0 chemical. And sort of coming to hydrodynamics, I think so since mean free paths are of order n, hydrodynamics is valid on length scales which are larger than n. Which is I think the caveat related to in any of these systems in which shear viscosity or conductivity is infinite. The validity of hydrodynamics is on like scales which are bigger than infinity. I don't know this.
Yeah.
Sorry. So is it that you can't use Q1? I mean, the normal charge.
Yeah, Q1 is just J itself, so that won't give me anything. I can use it, and this will just be equal to JJ, but it's not.
I see.
I was just worried whether anything else would appear.
Also, sorry, I'm getting confused. This is JX actually. We are computing the JX correlator. What's conserved is the J0, is JT.
Oh, that's true.
Not JX. Sorry, that's probably a better answer to the question. We are computing here like sigma XX.
That's true.
Always. So there's this JX, and the dot of JX is just integral of J0 is what's conserved, not JX. So here also this Q3, it has several vector indices. You have to pick the appropriate Lorentz.
And can you just intuitively help us see that JX, that from the JX momentum is 0, but the third charge is not 0. Is there some counting argument?
We didn't actually compute the overlap, but I guess the genericity argument is you don't expect it.
But there's no symmetry.
Yeah.
Is that quick symmetry argument to say that JX momentum is 0?
I think it's the particle whole argument intuitively. Mathematically speaking, I'd have to.
I was just wondering if some charge conjugations.
I was thinking that. Under something, J will flip sign,
but
momentum will.
Yeah.
That's
probably, yeah.
And so So when I was just trying to say, what I would like to see is that same argument will not make all of them.
All of them zero. But the higher spin currents would also
Possibly
satisfy
odd ones.
odd ones.
Yeah,
The odd ones.
Like
Yes.
JT.
Yeah, exactly. That will 3, 5.
Yeah.
Exactly. Yeah. Okay.
So all the even ones will be zero.
Yeah. But you also need to be careful because you are at finite temperature. So these higher spin currents, they're not exactly conserved. They're conserved up to like 1/n corrections, and all those you can take care of and it's properly treated in the appendix. You might have to modify the currents by some double trace terms and 1/n things and so on.
Sure. No, but it's
Yeah, and you have to make sure that the currents themselves, the charges don't have sort of order n thermal expectation values. You have to subtract off things to make them
I
zero.
understand that. But anyway, you're only claiming that this is non-zero up to 1/n connection.
Yeah, exactly.
So it's not that.
Yeah. But just to make the argument tight, like you have to appropriately correct.
I understand. But it seems intuitive.
Yeah. Okay, so that's all that I have to say.
I don't see how can you argue that there will be non-zero overlap only with a finite number of charges, like you are around a free theory, right? And you have
You can have infinite, that's fine.
but
The set can be infinite.
Is there a principle to say like what is the strongest bound that I can put in this?
It's a good. I mean, it's clear that all these contributions, it's a positive definite
Yes.
matrix. So intuitively, at least, the more charges you put into this thing, the better bound you will get. But also, it's not. We don't know if so. For example, in the paper we have a plot for d, right? This d as a function of lambda, it goes like something like this. It's 1 here and log 2 here or something like that. So you can compute it via these double integral expression that I wrote. But I don't know how to compute. Like let's say it's equal to this thing, or equal to. You can even ask whether there's a complete set of Q's which will make this inequality an equality. And try to compute this sum and see that it's equal to this. Might be.
Because in some sense, in this theory, all operators are the
Are the current. Right. But then you have to compute these overlaps and so on.
Interesting. And suppose I wanted to generalize this calculation to include any potential that should be.
Yeah, you could do it modulo the Schwinger-Dyson equation would be. So Son has a paper which is orthogonal in which he has 0 temperature but finite chemical potential. So he has done calculations of the JJ correlator in that system. And
It doesn't sound very difficult.
Yeah.
Right. Yeah.
I don't know of anyone who has done it with both T and mu.
But the partition function is easier to compute with both T and mu.
Both.
So
Yeah.
that sounds too tough.
Yeah, so-
Yeah, sounds possible.
Yeah.
Actually, I'm not sure. Yeah, sounds interesting.
It's just
Such a good.
we should ask ICTS for questions.
But-
Hi, Spenta.
No.
Yeah, I have a question. I mean, because you are calculating the 2-point function of the current, this is the reason why you could get away with saying that QA are conserved.
Right. Yeah.
So, if you had actually physically interesting higher point functions, then clearly this type of argument cannot be made because there will be one of some key corrections.
Right. Exactly. So this is, I mean, it's kind of a safe spot because you can make this argument within 2-point functions. And that's actually enough to get us a non-zero this Drude weight. But if you were trying to make such inequalities at finite temperature for higher point functions, you would fail precisely because these kind of subtractions and modifications to the currents I was saying, you would not be able to do. Yeah. Point very late.
So one of the things that is interesting about the large N limit is if you could apply to a n equal to 1, clearly this particular part looks like an artifact of the large N limit, right?
Yes, it definitely is. Yeah.
So you would not agree with really
Yeah.
you want.
Yeah, I think at n equals 1, these computations by Subir and Kedar, they already have like a non-zero DC conductivity. When they can compute it perturbatively in lambda only, like not to all orders in lambda. But yeah, I mean this sigma at DC is something number that you can like see in the waveform.
I don't expect a delta. Do they get a delta?
No delta function, just some numbers. It's like sigma of omega equal to 0 is some number. It has like some Riemann zeta function derivative and some 3.
But if they turn on a chemical potential again,
They'll get a delta function. Yes.
Yeah. Sorry. And why are you? You look like you're interested only in omega near 0.
And it's because of this, there was this Tudor weight that we could figure out all these things. But yeah, the paper has plots for plots that look like, or here you can have sigma xx, real part or imaginary part, or sigma xy, you can have a real part or an imaginary part.
As a function of omega.
As a function of omega over t and for different lambda.
And is there anything interesting to read out from them?
So, they have like a peak at twice the thermal mass. So that's one thing that you can read off. But
I was going to ask also. So these are conventional Fermi liquids or what? Can you figure out from here whether
what the Fermi liquid parameter like that ties up to the conventional lambda theory?
Yeah. Okay. Can you figure out?
I have a question.
Yeah.
Go ahead, please.
Can I ask a question?
Yes, please.
So one of the things we know about these type of theories which have fermion-boson duality is that for even a tiny amount of K, that is the Chern-Simons coupling level, or lambda, small amount of lambda, the theory doesn't have either fermions or bosons. So is there any, does your work give any diagnostic to this point? That really the spectrum of the theory is in terms of anions and neither fermions nor bosons.
Yeah, I mean,
Sorry, maybe someone will correct me. I thought what Sohn showed for his T equals 0 case was that it was more or less a conventional Fermi liquid, except at this point where it becomes a free boson or something, right? There was one point where it had to fail and it did. What is the story? Do you remember?
Yeah, I remember. It was basic. It's a question of energies. But suppose you take the suppose you he looked at 0 temperature chemical potential, and then he looked at it as a function of lambda. And if lambda was, he could only do the calculation on the fermion side, because the post-condensing phase is not understood calculation. Okay, and if he looked near lambda equals 0, he got the spectrum of excitations, for instance, was exactly like the spectrum of excitations with the Fermi illustration. But it gets deformed as at any finite lambda until you go to lambda near 1, and the answer looks very much like you're doing just a free like a post-condensing calculation.
Yeah, okay, that's.
So, but it's not like there's a special. It's not like lambda equals 0 is special. As you go to or lambda equals 1 is special. As you go towards 1, it comes more and more like a Bose-Case. It's quite incredible how it works.
but answering the Spenda's question, like anionic things, I don't think this calculation directly has any bearing to sort of phase exchanges and so on as you take particles around each other.
But maybe again, related to all these questions, suppose I take any one of your plots and I try to see how it evolves from lambda equals 0 to lambda equals 1.
Yeah.
Can you roughly
Yeah, I can.
Because lambda equals 1 has to be free boson.
Lambda equals 1 is actually empty theory because the n boson goes to 0. So all the conductivities actually become just 0.
No, but I take that coefficient.
Then yes.
I look at the structure.
For example, let me draw you the real part of sigma xy as a function of omega over t for different lambda.
Yeah, so first show us lambda equals 0 and lambda equals 1. I mean, ignoring normalizations.
Yeah. So lambda very small
Yeah.
is like this. Okay, that's something. The lambda equals 0.5 UA. Something like this. It's on the same plot, so this vertical scale is correct. And then lambda equals 1 basically becomes a flat plot with like a small bump. Like so lambda equals 1 will just be a pure line.
Lambda equals 1 is flat.
And all the contributions at lambda equal 1 are just coming from these contact terms.
should I? So it's flat and non-zero.
It's flat and non-zero. It's non-zero because of this, for example, for the fermion there's this 1/2 factor. There's already a plus 1/2 sitting in sigma xy.
So I should have known this. Should I have known that for free bosons the conductivity is independent of temperature, but that's not for free fermions. Independent of
So,
formulas.
sorry, are you plotting sigma x?
Sigma xy. It's a real part of sigma xy.
Xy is all
Xy. So this is the hall.
Could we do something more correct? Okay, whatever.
You want sigma xx? I can plot sigma xx.
Okay, but anyway, even for this, should I have known why you're telling me the free bosons have no structure, whereas free fermions do? I should have known this.
Which one is free boson? Which one is free?
Free boson is flat.
This is n. Okay, let me not say that. So this plot of real part of sigma xy divided by nf is this. Now, if you divide it by nb, then I'm not sure what the result will be. Here I'm dividing by.
I don't think I get zero. Just where that line is where.
That line is somewhere around 0.16. Now, I'm not recalling. So if you remember the expressions, there will be nf over 2. So there's this 1/2 which comes just from the parity anomaly, which is there for all of these plots.
Okay.
So I think that this line, the baseline is the 1/2, because any fermion you take is going to have that 1/2 contribution.
Let me just ask my question once again. What I want to understand is qualitatively does JJ differ between free bosons and free fermions? If you look at the shapes, forget these theories. Suppose I just calculate free bosons and free fermions. What do they look like? Then, if so, then it looks like it may have bearing on Stanford's question because it's going from one to the other.
At finite chemical potential, of course, they totally differ.
Because Fermi.
Yeah. And I don't know the boson theory is some sick theory.
Yeah, free boson just.
So let me plot it. Let me plot a different thing, which I think may be helpful.
Relativistic.
As a function of the Chern-Simons coupling, instead of as a function of omega over t, let me plot the non-dissipative Hall conductivity. So that's this one. So lambda goes from 0 to 1. 0 to 1. Okay. And omega equal to 0 curve, which is the DC curve, looks something like this. Okay. This value might be log 2 over 2, I'm not sure how to check. And t equal to 0 looks like this. So just like, so lambda equals 1 is where you expect the bosonic theory, and it's this monotonous function. This one is omega equal to 0. This one is omega equal to.
I'm sorry, Raghu. I'll just ask once again. I think it's Penta's question. The question is that the difference between free bosons and free fermions, the spectrum of excitations is roughly the same. The difference, if it comes about, is because one set is occupied by Bose statistics, by the formulas of Bose statistics, and the other is occupied by the formula of Fermi statistics. So you might wonder if what's happening in the middle is roughly that you get more or less the same spectrum, but occupied by some different statistics.
Okay, let me look at the formula.
Different occupation number.
Yeah, let me look at the formula and maybe come up with some.
Sohn's paper had some comments on something like this. He had an effective occupation number formula that interpolated between bosons and fermions. Yeah, which looked very interesting. Okay.
But I mean, more generally, isn't it a key question from the condensed matter point of view whether you get a system which is a non-Fermi liquid? I mean, I thought that was one of the things people wanted examples, controlled examples where you could get
A non-Fermi.
Yeah.
See, it would be interesting in this theory if you could incorporate 1 over n corrections. Because having a
but first, just in large n is the system. Suppose it was the case that it's a non-Fermi liquid. You might think that persists at least up to some order in 1 over n.
I think this system.
Whether n equals 1, which is perhaps most interesting, I don't know.
Yeah, it's also been a while since I looked at Sohn's paper, but he did say that what's a Fermi liquid? It's just like something. A non-Fermi liquid is anything which even differs from it in one aspect. So let's say the specific heat doesn't go like linear in T. You call it a non-Fermi non-Fermi liquid, but in all the other x minus 1 parameters it's the same.
Okay, I agree, but at least you don't have Landau quasi-particles, with that standard dispersion, driving most of transport or some of transport. I mean, that is the dumb Fermi liquid, right? You have the quasi-particles are
So let's
free,
see,
almost free up to
in
Landau.
temperature, for example, you would have that the resistivity goes like temperature squared, right? Is one of the standard results of Landau
Landau
Fermi
Fermi liquid, yeah.
liquid theory.
Right.
And here I didn't do the expansion to know like what the leading order, resistivity. I mean, the DC resistivity is infinite, so but as a function of temperature,
Yeah.
I just didn't connect it to.
No, but I'm asking whether. Actually, no, sorry, just one more small thing. Which is, you say Subir and Kedar already did it for the U1 case?
For the U1 case, perturbatively in the Hooft coupling.
Perturbatively. So I was just wondering whether they saw some.
They might have, yeah.
I don't know.
I mean, there are various things that people check when they check whether it's a Fermi. One is this resistivity, another is specific heat, or even these diamagnetic polytype susceptibilities and so on. But yeah, it's a system with fermions and with some interaction which you can solve at large n. We have the exact propagator for the condensed matter people. The first thing they always compute is the fermion propagator. Here we have it exactly. It was done like 2 years ago. And maybe even there you can read out properties like there is no lifetime first of all, so there's no lifetime does not go like temperature squared. So that's why the interesting things for Fermi versus non-Fermi will come once you put in the 1 over n corrections.
Just to say that our soul had some quite interesting answers at large.
At large.
Some leading order large. In particular, you have this thing they interpolated between a Fermi-Dirac distribution function for excitations and a Bose distribution function.
I somehow thought I must be wrong, that it was sort of a Fermi liquid, but except for what you're saying.
I think not.
Somehow confused.
If you're seriously interested, I'd be happy to hear a journal club.
I'm happy to, yeah. Please do, no? Isn't it one of the nice physics payouts we could get from
it's
your
so interesting.
Chern-Simons work?
From our Chern-Simons.
I can only
His own
Okay. But,
I could do this Thursday if there's interest. Okay, no, we'll do this.
One point, maybe if people are still interested, we can talk about lunch. There's a nice reason which was first Zohar told us is why chi for the fermions has to be 0. I mean, we are going around with this log 2 over 2 and confused whether these two objects are the same. But there's like a gauge invariance argument for why chi has to be 0 for the case of the fermionic theory. Because you reduce on the S1, right, of the thermal S1. Then what this chi corresponds to in sigma xx is a term in the background gauge field which is b squared, bx squared, right? Because it's sigma xx and it's a static contribution in the Euclidean path integral. And we know that the fermion on anti-periodic boundary conditions is gapped. So therefore the reduction is analytic and gauge invariance prohibits a mass term for the background gauge field. So you cannot have quadratic terms in B, this B mu, which I wrote down. And that argument is already enough for you to conclude that this chi should be 0 for the fermions. But yeah, that's a separate thing. It also helped us to get to the correct setup. And for the free boson, free massless boson, you cannot make that argument because it's gapless. So therefore there is no analytic control and you can get a mass term for the gauge field and you get this B squared term. Okay, thanks guys.
Any concluding comments from ICTS?
Thank you very much.
Thank you.
Thanks.
Thank you. Bye. Bye, Smenta.